By the way, did you hear a good news? No? Me either. Lately, not many. So, we should concentrate on matters at hand, physics. That's it. What is a definition of that thing you answering about? Lever arm? A lever arm is, yeah. Yes? Well, technically, the shortest segment, this line has no ends, and the segment is a part of a line between 2 points. So the shortest segment and the shortest next step, geometry, means it has to be perpendicular to the line of action. And which is well, out of 7 fits the best. Which did you choose? Yeah. 3. Yeah, no doubts. You just have to follow a definition. If we have a point which represents an axis, if we have a vector which represents a force, any type of force, we have to extend the force. Again? Yep, it's today, again, everything is red. I don't know why. Blue is red. Even black, I believe, will be red. Yep. Well, there are forces stronger than we are. And now we need to draw a line which is the shortest. It has to begin on the axis. It starts at the axis, and it has to follow toward the line of action, not toward the force. The force might be too short. It has to go to the line of action. What about yellow? Still red. Is this perpendicular? No, so wrong. Plus it's too long, we still can make it shorter. Yeah, so we just have to take a protractor, very accurately draw a segment which is perpendicular. It has to be 90 degrees here. And according to a definition, that's what we should call the lever arm. The lever arm, again, technically, is a shortcut. The full name is a lever arm of this force relative to this axis. And in this situation, it was number 3. So this is just a review. Okay. Please do this. Calculate, you see, in quotes. What does it mean? This word means when we actually able to use numbers and calculate to a number, we do that. Otherwise, we write an expression which represents that variable and which we can use to calculate that variable if or when all other important values are given. So you should keep copy a picture. What I want to try to do is just to reset the system quickly. So please take a snapshot, mental snapshot, so you would remember the picture. Now, the text of this question doesn't specify which of the elements is a wall, a rod, and a string. This is a part of a reasoning which you're supposed to figure out using your life experience and common sense, right? Okay. I will try to do something about this. I want to keep what I had. I want to save this. I want to close this. There are two ways to fix electronics. Only two. First, reboot it. Second, use a hammer. So let's hope you're not there yet. And this is one of the bad consequences of democracy. Because people do different things and don't talk to each other. Software, hardware, different companies. That's why we need a strong ruler. All right. All right. Okay. Sometimes I wish praying would help. In physics. Okay. Nope. Still. You see? It is what it is. So, relative to the hinge. So here we shouldn't even think about choosing the axis it's given to us. So this is the axis. And we have a triangle like this. This line represents what? Well, how do we know? What's the most common feature of all walls? The vertical. If it's horizontal, we call it floor or ceiling. So, wall. Is this a rod or a string? How do you know? Because it's not a string. And why do you know that thing is a string? Why? How do we know that this is a string, not a rod? Cannot hear you. Say it. You're right. Specifically, please. So the string has to be horizontal. The only horizontal line is this one. So this is a very, very kind of simple, trivial, but very important exercise of translating into words everything you see and observe. So rod, string. Well, okay. Which lever arm do you want to do first? Or which force? String. All right. So that's the axis. That's how the force of tension points. So what's your lever arm for the force of tension relative to the hinge? Can you tell me, please? Well, lever arm has no direction. Lever arm is a certain distance. And in this situation, we use variables for different distances. So for example, what variable would you use for the lever arm of the force of tension relative to the hinge? Do you have your own picture? So just look at your picture and what should I do to help? I like myself. Yes, I'm always helping myself. So what should I do to help myself to see the lever arm? What's the next step? To what? Like this? You want to say something? Say it. Draw the line of action. So if you don't do that, that confuses you. You have to follow the steps. The next step is drawing a line of action. Line of action is just an extension of the force. You have to do that step, you know. If you don't do it, you don't get to the end. If you want to boil some water in a kettle, you have to pour some water in a kettle, then put it on a stove, then turn it on. If you do it differently, turn stove, then put the kettle, and water runs in a sink, that's it. It's not going to work. So you got to do it in the right order. That's it. Next step is to draw a perpendicular. So next step is to look at the picture and say, what does it represent? What variable does this represent? This H. So the lever arm of the force of tension relative to this axis in this picture represented by, could have been any other letter, but H is like height. Yeah, for this point is higher than hinge. Yeah, that's it, nothing else. But it could have been a number, 30 centimeters, 20 centimeters, or something else. Okay, so what about, now I want to say, what about contact force? Does it exist here? Does it act on the rod? The contact force. You have to show all forces. Yeah? There is a force of tension. There is force of gravity acting on the rod. And the contact force, where does it act? At which point? From what to what? On the rod. What do you think? What do you think? The contact force, does it act? Where? Where does it begin? If I want to draw a vector, which point should I use at the beginning of the contact force? The hinge, which is the axis for us. Something like this. So now I want to say something about the lever arm of the contact force relative to the hinge. Please tell me something specific. Yes? Why? That is absolutely correct. Equals 0. So again, if we want to draw a picture for that, that's the axis, that's the force. We can extend the line. However, still, there will be no distance between the axis and the line, 0. And the last force is force of gravity. Same axis. Now you gotta repeat the procedure and tell me an expression or a value, well, in this situation, of course, an expression, for the lever arm of the force of gravity acting on the rod measured relative to the hinge. I would ask you again to send me a picture, but not today. 60 pictures. It takes a lot of time to process. I still have to finish writing the exam. So, well, what do you think? Yeah, you reacted, so it's you. A string is a word, it's not an expression. It should be algebraical expression based on variables presented in a picture. Capital H, capital L, lowercase l, and maybe some coefficients, 1, -7, square root of pi, or whatever. Little l. This is what we need to do. First step, I forgot, only read today. Second step, and we need to process the same actions in the picture. That's supposed to be the lever arm of the force of gravity relative to the hinge. Okay? This is it. Oops. Lever arm of the force of gravity relative to the hinge. So, what expression should I write? Little l? What do you think? I don't see any theta. No, no you don't. No you don't. What do you think, gentlemen? Well, it is 90 degrees. What do we know about this point? So this point divides the rod in half. And if we extend this line up and down, this, well, it's not very accurate in my picture, but this point, what does that point do? Also divides in half the length of the string. So, what should I write? For the lever arm? What do you say? L over 2. Because in this triangle, we know all 3 sides, we don't need any angles. We need an angle if we only know 2 sides. Yep.
How do we know that the point that the rod is exactly at half is also the point of the stream? I'm having a hard time visualizing.
Because you're looking at my picture, which is not very accurate. You have to draw your own picture using a ruler and a protractor. And that's the only way to actually do it. Unfortunately, again, something happened. I cannot insert, I don't have that thing, which used to be at the bottom and allowed me to insert extra slides. Well, I'm just going to try to draw here very accurately a triangle like this. So, and if this point divides the rod in half and you direct a line vertically, so what does geometry say? This angle equals to this angle is equal to this angle, 90 degrees, 90 degrees. So you can draw an additional line like this, for example. And, well, so that .90 degrees, so 90 degrees. This side should be equal to this side. And on the other hand, this side should be equal to this side. So these sides should be equal to each other. Oh, I love this. 6th grade geometry. I almost forgot how it works. I had to think about it. So will you, in a similar situation. And this is an example which stresses that sometimes things are not about physics, it's just about good drawings, good picture, and remembering some stuff from geometry. That's it. Because from physics, we used only a definition of a lever arm, which says extend and draw perpendicular, extend and draw perpendicular. And the rest is in the picture, in the angles and distances. All right, so I use only some of the pictures which I want to mention. I've seen many good pictures also, and actually you can find, since they had no personal information, they're on a blackboard. Only one person wrote the time, and I asked everyone. I asked, please write the time to your picture. All right, maybe it was time when I was speaking Russian, okay? So what's wrong with this? Has to be equal to 0. It's not an equation, it's a definition of net torque. Torque balance equation says net torque equals 0. Now, here, you cannot add magnitudes, because if you add in magnitudes, you can't make it equal to 0. Now, same here. This is not a torque balance equation, this is a force balance equation. Forces, not torques. Here. That's what caught my eye. I don't see those distances. So if you use some distance in your equation, it should be a part of your picture, because otherwise there is no reference and there is no way to make a conclusion. Is it right? Is it wrong? Here is the axis. This is actually a good diagram, but the choice of the axis, I just want to say sometimes is not convenient because we choose the axis differently, and our equation had only two terms. This has 4, and 4 is just more than 2. Yeah, so it's harder to do it. That's it. All right, go back to this situation. Again, this is what is happening. We just let it go. So we are here very lucky. We have 2 eyes. So one eye should be on the screen, second on here. So you should be thinking about the problem. And this is what you saw yesterday, so it's not a big deal. So if we let it go, they both travel faster and faster, but this makes rotational motion, and this makes translational motion. And I want to use this opportunity to illustrate how the mass distribution affects by moving away these weights. Thank you. By moving away these weights, I do not change the mass of the system. I do not change the mass of this wheel. I just change mass distribution or density. So I move the masses closer to the edge, to the rim. How should this affect? Now I have to even. How should this affect the moment of inertia?
Moment of inertia will be grading.
The greater increases, but if inertia increases, how should that affect the motion? Motion. How should that affect the motion? Increase? The more inertial, the harder to change the speed. That's what inertia means. So we should observe a slower change. It should take more time to reach the ground from the same height. And we just need to solve, as an example, this problem. This problem is a little bit more complicated than your lab problem, which you've done already, most of you, because it involves friction. So what do we do? Well, a free body diagram for this object, a torque diagram for, what is it, disk. We know that, well, technically this is a different force because it points differently, but we know that an ideal string doesn't change the magnitude, so we just call T the magnitude of the force of tension. Now we know it's going to spin clockwise, and this travels down. Words spin, travel, they describe the motion. But now we also know that in this particular experiment, it's going to be speeding up. So angular acceleration points also clockwise, linear acceleration also points down. And now friction happening here. It does provide some torque. And we know that the magnitude of the torque due to friction should be equal to 1/10 of the torque due to tension. How do we know? We can read. But torque also has a direction. So please tell me, what do you think is the direction of this torque? You say so? Yeah. To what? So, and that is correct. That's how we describe the direction. Friction always opposes the motion. So if we had any friction acting on this weight, it would be opposite to velocity. If we have a friction acting on the wheel, it will be opposite to angular velocity, and that direction has a name. Counterclockwise. There is no equation. I'm just saying that if velocity is clockwise, friction opposing the motion should generate torque, counterclockwise torque of friction. Yes?
I meant the torque of friction.
This one?
Yeah.
I try to. This is what I read, and this is what I write from that. Just again, today is a special day. Everything red and. So now we have to write equations. We did it yesterday, but yesterday we did it without friction. Now we just have to repeat. So y and the positive z direction, actually, z. How does it point? At us. This dot represents z-axis. So relative to y, what do we have relative to y? We have tension minus gravity equals now, when I write equations like this with the minus, that automatically means all variables represent magnitudes. Again, just to refresh, this is how we used to write it. And Ty is positive, Gy is negative, and Ay is negative. All right, now Z. Clockwise means positive, so we have actually, clockwise means negative, counterclockwise means positive. We actually have one positive torque, which is due to friction. Now minus torque due to tension should be equal to the rotational inertia, moment of inertia, times z component of the acceleration, which is negative. So in this equation, also, I use the same agreement. All variables already magnitudes. And now we can add, so we had one equation already. That's number 2. That is number 3. And now we can add the equation number 4, which relates angular acceleration and linear acceleration. We also call it tangential acceleration. So this is something which, again, if you don't have an equation sheet handy, this is the rule of thumb. Rotational equals linear over r. So rotational acceleration that's it. Any questions? This is a standard procedure. Free body diagram, a torque diagram, directions very important. Negative component means use a minus with the magnitude, and at this point, the rest is algebra. One more example. Now we actually want to lift this weight. So if I start from the bottom, it's going to lift itself. So we got to apply an external torque. Yeah, it's like pulling a bucket with water from a well. It could have been a hand, a handle, a motor, anything, doesn't matter. We just need to remember there has to be an additional torque responsible for this motion. That's it. So what will be our diagram now? Well, how does velocity of this box or weight point? Now it's up, yeah? And it travels at certain acceleration. It's speeding up, acceleration points up. But forces still point in the same direction as before. Gravity points down, tension points up. Here, force of tension still acts down as before. But what is the direction of the angular velocity of this disk? If we look at the picture, relative to you, it spins. How do we call that direction? Counterclockwise. Counterclockwise. So what's supposed to be the direction of the external torque? Counterclockwise, because otherwise it wouldn't be possible to make it rotating in that direction. So we call it applied torque, for example, or torque a motor, engine, handle, hand, doesn't matter. And there is some friction, so what's supposed to be the direction of the torque, of the frictional torque now? Clockwise, because it's opposite to velocity. This is our picture now. That's it. Everything is in the picture. Now we just have to follow the rules. Yeah. Counterclockwise means positive, clockwise means negative, up means positive, down means negative. So, tension minus force of gravity acting on the box equals mass of the box times acceleration. Now there's no minus for acceleration, points up. Okay? This is positive z direction. Right-hand rule out of the screen. So which torque is definitely positive? The applied torque. The frictional torque is negative. What about torque due to tension? Positive or negative? Of course, relative to the axis or negative. What about acceleration, positive or negative? What do you say? Acceleration, positive. Well, we know how to relate these variables. And this is the fact, this is based on the fact that the string doesn't stretch, right? So this point in a second travels exactly the same distance as the weight travels in a second. And also where we know, well, some additional information is given here. The acceleration is equal to 0.1 meters per second squared, and the friction provides torque, which equals to 0.1 0.1 of the applied torque. And that's it. One more thing, which I didn't do last time. This variable, I, a moment of inertia. What equation should I write? For which shape? For the disk. Lucky us, it doesn't matter if it's C or K. It's still 1/2 times the mass times the radius of the disk squared. That's it. Yes?
How did you add the direction of the tension?
I do not understand the question.
Do you have a force of tension going?
Acting on what?
Yeah.
Acting on what?
One is acting disk and one.
Which equation do you refer to? Equation written for the weight or equation written for the disk? Okay, if you want to write an equation for the disk, why do you think about forces acting on anything else? Don't do that. Thinking really not helping you in physics. If you write an equation for that given object, don't think about any other objects. Use only forces acting on that object. That's it. And then you wrote that equation, you can forget about this and move on your attention to the next object. And when you do that, you forget about everything else. That's it. Don't try to think about many things at the same time. That usually leads to confusion. And again, physics is done. The rest is some algebra. Okay, very quickly. A solid sphere, what does this word mean? It means we cannot use that equation 1/2 mr squared anymore. We will have to use an equation for a different shape, 2/5 mr squared. And it was slowing down wherever in 10 seconds. So what was happening? A sphere spinning like this, for example. Doesn't matter. So the word sphere immediately means this is what we need to know. Mass, diameter. So if I want to calculate the moment of inertia for this particular sphere, I should use a form factor, mass, and what number should I square? No. You see, you missed this word. 1/2 of a diameter in meters, so 0.25. Just keep an eye on little things. Now, all right. So let's say it was spinning this way. So we want to stop it. So we apply, I don't know. So it was spinning, and we want to stop. We apply an external torque, friction, for example, and it stops, or maybe just slows down. Yeah, it slows down. The initial angular velocity was equal to 60 radians per second. The final angular velocity was equal to 2, not 0 radians per second. So we just wanted to slow it down. And the time to slow it down from 60 to 2 was equal to 10 seconds. So what are we looking for? Okay, magnitude of that force, which was used to slow it down. Well, technically we also have normal and gravity. That's our axis, so the only torque responsible for acceleration, angular acceleration, is that due to force, so force of friction times radius. That will be the magnitude of the torque, and that should be equal to I times the magnitude of acceleration. So the force will be equal to this times this divided by this. And what do we do about magnitude of acceleration? Acceleration always changes in the velocity over time. Linear acceleration changing in linear velocity over time. Angular acceleration change in the angular velocity over time. So we're just making connections. That's it. I forgot, sorry. Physics is done. Yes?
What sign do we say?
Say again?
What sign?
You see, I'm looking for clues which helps my life easier because I'm looking for the magnitude. I don't really care if it's spinning clockwise, counterclockwise. I just calculate magnitudes for everything. Well, if we use my picture, my hand actually is on the left side of the wheel. So here, where I touch it, it should slow it down. So the torque due to friction should oppose angular velocity. My angular velocity points clockwise, so the torque should be counterclockwise. Actually, that means acceleration in my picture should be counterclockwise. All right. It took a little bit longer than I thought, but we are done with this. Moving on to angular momentum. Remember, in the past, we've used Newton's second law to derive law of conservation of linear momentum. We said when net force equals 0, total linear momentum of a system remains conserved. Now, don't read that because it doesn't really matter. This is for me, so I wouldn't forget to say something about it. We can apply the same kind of reasoning to rotational motion. Still, we can use a similar equation, and we can say when net external torque equals 0, this variable is supposed to be conserved. There should be no change. If something is conserved, it's important to us, which means we give it a name, and then we study its property a little bit. So this product, this is the moment of inertia, and this is angular velocity. This product has a name, angular momentum. And now we can say when net torque acting on the system equals 0, angular momentum of the system should be conserved, shouldn't change. So no matter what's happening inside the system, total angular momentum before and after is the same. That's it. I forgot about this thing, but it's too late now. You know, in theater they say, if there's a rifle on a wall, it should fire in the play, but it's not in physics. I moved on. So now it shouldn't abstract your vision. Well, question. I'm here, I'm back. So you got to make a mental picture of the situation. This is a disk, a turntable. It is at rest. And I'm going to shoot at it like this. Oops. That's the bullet. It flies. Now, of course, I will shoot at the disk, and you will have to tell me what do you think should happen. And that is not a tricky question. This is a common sense question. You know how much money we spend on this? Millions. Oops. And years of practice. Oh. All right. This lesson will be much longer than I thought. Well, I've got 2 more bullets, so. One more. You know, today everything like Friday, but it's Thursday, something is not right. Well, now you've got a mental picture. More nightmares. So, what do you expect to happen? The law of conservation of angular momentum tells us what should happen. Well, we just need to do the same, to use the same strategy we used for linear momentum. First of all, what was happening before the collision doesn't really matter. The history doesn't matter. So right here, right now, the bullet is right before the catcher. And then right here, right now, the bullet is in the catcher. We used to have a very similar situation. We called it the ballistic pendulum. This device also can be used to measure how fast bullet can travel. So it was traveling like this. And now they travel together. The problem is, if we want to use the law of conservation of angular momentum, we shouldn't be using linear variables. We should be using angular variables, because the law says, well, I1 omega 1 initial plus I2 omega 2 initial should be equal to I1 omega 1 final plus I2 omega 2 final in general. So what is I1? That should be the moment of inertia of this bullet. But when? Where? Again, history doesn't matter. The catcher doesn't know how the bullet was traveling. For the catcher, the bullet could have been just traveling in a circle like a ball. So for the catcher, the moment of inertia and the angular velocity of this bullet is exactly the same as it would have been the moment of inertia and the ball traveling like this. History doesn't matter. So, and for this instant, when the ball is here, it's a small mass, so we just have to write mr squared. And there is a relationship between angular velocity and linear speed, which we used before several times. We just write it again. So disk has standard moment of inertia, but initially it wasn't moving at all. Afterwards, they start moving together. So they actually have the same angular velocity. And afterwards, actually, well, because this is a standard absolutely inelastic collision, they travel as one whole object. So this is how we can set up our law now. So from everything we've used before to prepare the law, what should we write? mr squared. That's this term. Times angular velocity, which is v over r initial, plus 0, because it wasn't moving, should be equal to, well, what's the total combined moment of inertia? Little m r squared plus 1/2 big M r squared times that final combined angular velocity. At this point, all we have to do, plug in numbers and solve it. In terms of direction, of course, if it hits here, the catcher axis is going to start traveling in that direction, as you saw. It doesn't really matter in this situation if it gets caught or bounced back. For the disk, it doesn't matter. Disk still will travel. That final counterclockwise, yes?
I don't understand why you can say the bullet has an angular velocity. And especially, why can the angular velocity be equivalent to the radius of the disk?
Angular velocity cannot be equivalent to radius.
Why can you use the radius of the disk as far as the angular velocity of the bullet goes?
Well, here is the part where we have to use our imagination, because nature doesn't care about us or how we look at it, right? So if you look at this ball, right here, right now, relative to you, it travels that. Do you know if it was shot on a string? You know, because you see it. Nature doesn't. So for the nature, these two objects, this and this, identical here and now. The history doesn't matter. So you saw the bullet flying, 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 flying. Yeah. If you had a little ant slipping here, and just before the bullet hit, opened the eyes, what happened? That guy wouldn't know how the bullet killed them. Really? Yeah? So for that guy, it wouldn't matter if it would have been a ball which was rotating initially like this. And if it doesn't matter, that means we can apply exactly the same mathematics for both. There is an official definition if you want to dig in. It's called the angular momentum of a flying bullet. Google. Yes? Absolutely. Instantaneous, here and now, because nothing before that matters. The history doesn't matter. So that's the reason, that the history doesn't matter. There is a physical equivalence. If instead of shooting a bullet, we would use the ball, which would hit this catcher with the same speed at the same point, that wouldn't matter. That's why we use this equation. That's kind of, yes. Why? In all these equations, I use the same variable r for the radius. So this r represents the radius of this disk, which is a part of this equation. However, because we shoot that way, we shot, because the catcher is here. For the bullet, this distance from the axis to the location of the bullet is also r, but that's only for our convenience. Technically, of course, I could shift a catcher somewhere else, here for example, and the bullet would be flying like this. In that situation, for the disk, we still would have to use this equation, but for the bullet, here we would have to use smaller, different distance. There is no radius of the bullet. There is radius of that fictional circle we imagine for the bullet to make. In this situation, that fictional circle has the same radius as the disk has. It could have been smaller. That would change this and this. That wouldn't change anything related to the disk. But don't worry, that ant survived. All right. Yeah. I'm not going to finish everything I wanted to do today, but we still have tomorrow. I don't have a clay here, so there's a heavy disk. Instead of a clay, I have something heavy, which heavy enough to stick to the disk. So it's spinning, and you should have expected that. It's a heavy metal falling on heavy metal. It's heavy metal, very heavy metal. Another nightmare. All right. So what did you see? What happened? Did it change the speed? Oh, you didn't see. Okay. No. Be ready now. I think I broke it. So it was spinning fast, and after this piece of clay fell on it and it get attached to it, what happened? Slow down. Why? Because of the law of conservation of angular momentum. Very similar to the previous situation. So what was happening before? This is a top view. So this disk was spinning. Nothing else. So if I want to calculate the angular momentum of the disk, which now is angular momentum of the whole system. That should be equal to I times this, which is 1/2 mr squared omega, well, initial. Now, well, in this situation, we actually put it here. Could have been different distance, doesn't really matter mathematically. So, and we saw it will slow down. The final is not equal to initial. So what do we do now? Final should be equal to, well, they travel, again, that's a completely inelastic collision, travel together as one whole object. So we should write I1 plus I2 times omega final. That's it. I1 for the disk, still the same moment of inertia plus. Well, this piece of clay or this weight supposed to be considered as small mass relative to the size of the disk. And for the small mass, the expression for inertia is mr squared. And in this situation, this r is equal to the radius of the disk. That's it. Same. Just a different mass. That's not the law of conservation of angular momentum yet. It's a preparation for the law. What does the law say? The law says the initial angular momentum must be equal to the final. That's what the law says. This is the law of conservation of angular momentum. So what should we write? We should write 1/2 mr squared times initial angular velocity should be equal to 1/2 mr squared plus little mr squared times final angular velocity. Yes?
So do we not take account initial momentum of the weight that we're dropping?
It wasn't moving. No, it wasn't moving. It wasn't moving. So that's why it's 0. That's okay. And if you solve it, you see, you have to divide by a larger number. So as a result, the new velocity is lower, as we saw. Well, there are many, actually, maybe this is a good time to finish this lecture. There are many experiments related to law of conservation of angular momentum. For example, there is a toy for sale. People play. They drop a ball. It was moving slowly, but when the radius of the motion was smaller and smaller, it was moving faster and faster and faster and faster. Why? Well, because when we make it move closer, we decrease I, and to compensate decrease in I, we have to increase omega. Another thing, again, a toy, you can buy it. And the demonstration like this has a name, a dying star. Stars, neutron stars, eventually they contract in size. And when they get smaller and smaller, they move faster and faster. What is opposite to the experiment here. And actually, the, neutron stars, they beam radiation, X-rays, and we can measure how fast they spin over time, and that gives a lot of information on the universe. Toy. Broken. Working. Why? Can't tell you, it's very complicated. This is a gyroscope, a toy gyroscope. A toy gyroscope, based on the fact that when something is spinning fast, it wants to keep angular momentum conserved. So this is more like a commercial gyroscope. We just need to spin it. You know what it is? A compass. It tells us where the north or the south is, but sometimes a compass is not very reliable to show a direction. It might be affected by other magnetic fields. But now this disk should keep the angular momentum no matter what is happening to it. So this is a navigation system. You can move in space, but it will be pointing at the same direction, no matter what. So if you're in a submarine or in outer space where there is no magnetic field, still, as long as it spins, well, of course, friction kind of makes it die out eventually, but as long as it spins with the same velocity, it always points in the same direction. This is another gyroscope, which why doesn't it fall? It's like a top. It wants to keep the angular momentum. Well, here the situation is more complicated, like with the top, because technically there is net force, gravity. So it's not, so that's what makes it also spin. And the mathematics for this experiment actually, simple experiment actually is very complicated, but still it is based on the law of conservation of angular momentum. Now, I've got 6 more minutes. Hopefully, I'm not dying today. But there are 2 more demonstrations which I have to do, and they were dangerous. I might fall, I might hurt myself. I don't want to hurt myself, but I have to do it anyway. I was hurt very badly. On November 9th, 2016. This wound is still fresh. All right. Catch me if you can. I think I'm going to stay here forever now. All right. Ooh. Ooh. Now I can stop. Oh, 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 oh. Oh. That happens. You see? Dangerous. Don't worry, not my first time. Well, what was happening? First, I can tell you what I forgot to do. I needed to put stoppers under the wheels. And I have them. I just forgot because of the time. So, when the wheel was spinning, when I changed the direction, I started spinning in opposite direction. When I stopped, I had to compensate the absence of it by spinning in opposite direction. Well, unfortunately, it's not very steady balanced. So, and I didn't do what I supposed to. So I almost died today, but but now I see the light. All right. Any questions? Don't do that. Now, I didn't ask you this question because this is a standard demonstration, which I'm not going to do. You never can see this online, but you can find that online. So what's happening here? When she moves her arms closer to her body, what does she change? Does she change her mass? No. So what does she change? Moment of inertia has no radius. The value of the moment of inertia. How does she change it? When she pulls arms closer to the body, what's happening to I? Decreases. We know when we move masses away, it increases inertia. When she moves mass closer, it decreases inertia. But in order to keep the product constant, what should happen to velocity? And you've seen, if you've ever watched skating, figure skating, you saw it many, many times. That's a standard kind of. All right, so now that's me. Now you've seen everything. That's also me. And not going to ask this question. I just want to show you the equation which you can use for, torque does work. If you ever try to start the engine, motor, you have to yank it, so your energy get transferred into this rotational motion. And if you want to calculate the work done by torque, we can start from standard equation for the work done by force, but rewrite it using rotational variables. Just multiply by the radius and divide by the radius. This gives torque. This gives angular displacement. That means I've got 1 more minute, and I just want to give the answer to this question. These are different angles. Same letter, and people confuse. This is the angular displacement, and this is the angle between velocity and force, or between angular velocity and torque. And this angle, for rotational motion, has only two options, 0 or 180. If this spins counterclockwise and torque counterclockwise, they parallel, this angle is 0. If object spins counterclockwise but torque, another force, is clockwise, the opposite, this is 180. So for the work done by torque, this number, either 1 or -1, that's it. All right, I'm going to pick up from this tomorrow. And tomorrow we will definitely have time for questions and answers, so please prepare. Whew.